Well, welcome everybody. So my name is Vijay Balasubramanian, and I'm a member of the General Governing Board of the Aspen Center for Physics. I've been in this position on the board for about 12 years now. So welcome to our public lecture series. So this is the lecture series sponsored by the Nick and Maggie DeWolf Foundation. They've been very generously supporting this lecture series for about 30 years now. So every winter, we have a sequence of lectures like this. So please come throughout this winter and come next winter and the winter after that, all of that. We also depend for these lectures on the generosity of the speakers because they volunteer their time. We're very grateful to them. And that's part of the way we as physicists are attempting to give back to this wonderful community that supports our center here in Aspen. So the public lectures in the winter are part of what we call our winter conference series. So the way that works is that every week there's a different topic at the cutting edge of the field, particularly very new things people are trying to study. About 100 physicists from around the world will come to discuss and talk and come up with new ideas and work on them over here. And of course, they also take advantage of the gorgeous outdoors. It's always been part of the attraction, having a Center for Theoretical Physics in a place like Aspen. You can get out there and hike and ski or whatever else you'd like to do. So as Emily mentioned, I myself have been coming here for about 25 years. I can testify that this is like one of the very best places in the world to be doing theoretical physics. It's a really great thing we have here. This week, we have a conference on a fascinating, absolutely new area of physics, inanimate materials that learn. Learning is something usually associated with sort of animals and, people are animals too, and things like that. There's actually inanimate materials can be made to learn. So we're very fortunate to have today as a speaker one of the true pioneers of this fascinating new field. That's Professor Andrea Liu, who's my very distinguished colleague at Penn. Professor Liu is renowned for her work on complex states of matter, all the weird things that can happen, so the complicated interactions between the things that make up these complex states of matter. He's received many awards, including election to the National Academy of Science, which is one of the highest honors that the country can bestow on a scientist. So she will tell us today about how physical systems can learn by themselves. So without further ado, I give you Professor Liu.
All right. Well, thank you, Vijay. It's really great to be here, and thank you all for coming. And please, if you have questions as I talk, please just speak up. It's much more fun that way. Don't hesitate to interrupt me and ask questions as we go. So sub-theme of my talk is you'll see. So the first part of my talk will be how AI can help physics. So it's not, this talk is, asks not only what AI can do for physics, but also what physics, that's the second half, what physics can do for AI. So, let me just go ahead and get started on what got us going on this problem. Was thinking about the brain vasculature. Okay, so this is the system of blood vessels that feed your brain. And it's incredibly important. The brain actually uses 25% of the oxygen that comes in through our lungs and uses that oxygen to support brain function. So, so right now, I am talking, okay? I'm using my speech cortex. My brain vasculature, as I started talking, adjusted to feed more oxygen to my speech cortex, okay? To support that. And it did that by dilating some of the blood vessels and contracting others. Okay, so, and it did that in real time. Okay, similarly, I hope you're listening, and so you're activating your auditory cortices, and your brain vasculature is supplying extra blood flow, or extra oxygen to your auditory cortices. So, so that's an interesting thing because blood is coming into the brain through the arteries. Okay, there's a source of blood here, and then what your brain vasculature is doing, it's a network here of about 1 million blood vessels that are adjusting their diameters or effectively their resistance to blood flow in order to deliver extra blood flow to a certain spot. Okay, my speech cortex. It's the desired output. Okay, and so and that's actually the basis for a very popular form of functional MRI. Measures actually the oxygen. So that's how they can tell which parts of the brain are active. I have to apologize. I have a bit of a cough. I'm not sick. I had RSV, but I'm over it. But this is just lingering asthma. That. Okay. So we started thinking about, okay, how could we design systems that did this? That this is really an amazing thing that the brain does. And when we were thinking about this, we realized that computer scientists had figured out a very similar problem. So, before I do that, let me say, we wanted to do this. We wanted to figure out how to do this, but we didn't want to work on the actual blood vasculature of the brain. That's too complicated. Okay, so we turned this into a simple model. Okay, so we thought about a simple model, which is a network. Okay, it's a network of these lines, which are you can call edges. You can think of them; those are the blood vessels, like little pipes. Okay, that carry fluid, and they're connected at nodes. Okay, these dark spots are these are the junctions. Okay, of the pipes. The brain has about 1 million of these edges. Okay, 1 million of these. It's a lot. And so, here's a network. It's not the same network. It's a much smaller network. But then we said, okay, this system, how could we adjust the resistance of each pipe to flow? Okay, so that if given an input, okay, across here, this pipe, how would we get a desired output across that pipe? That was how we turned it into a simple model that we could then start thinking about in terms of physics. Now, how do you solve that? So we realized that computer scientists had figured out how to solve almost the same problem. Okay, so that's what happens when you train a neural network, for example, to tell the difference between cats and dogs. What are you doing? You've got a bunch of inputs, which are pixels of an image. Okay, that's like the blood coming into the arteries. And then you want a desired output. Example, one if it's over here if it's a dog, one over here if it's a cat. So you want a desired output. That's like extra blood to my speech cortex. Okay? And what the idea is we want to figure out what is the network that will give us the desired output. If you start with some random network, a neural network, you send in the inputs, it's not going to give you the right outputs. You have to train this thing. Okay. So how does that work? How do they train it? So we realized we could train our networks to do this in the same way. Okay. So this is how you train an artificial neural network. What you do is you set up, it's called a learning cost function. Where you compare the output that you get. So you apply the input, you give it the image, look at the output. Probably not right? It's not going to be correct. Compare that output to the output that you want for each of the outputs. And you don't know which is bigger. You square it to make sure that it's not negative. Okay. And then you minimize this thing. You try to bring this to 0, because if it's 0, the output will be the desired output. Okay. So, and you do that by adjusting parameters in the model, okay, which are, things having to do with the nodes. All right. So you adjust these. And how do you adjust these? What you want to do is you want to go downhill on this thing. Okay. What's going downhill? Skiing. Okay. That's something that we all know about. Okay. So let me explain this process. It's called gradient descent, which is basically skiing. Okay. So the idea of gradient descent, so when you're skiing, right, what are you doing? You're moving downhill in a landscape. Okay. It's a landscape that's a mountain slope. And so you've got altitude, which is the altitude of the mountain slope where you are. And what do? You adjust latitude and your longitude. Those are what I'm going to call learning degrees of freedom. Those are things that you can adjust. They're called degrees of freedom because that means you can adjust them. You adjust your latitude and longitude, you go downhill. Yeah.
Right. But could I ask you to stand on this side for one?
Yeah, that's that thing. Yeah, the thing. Okay, yes. All right. I had to adjust my latitude and longitude. Okay. All right. So skiing, I'm sorry to tell you, is really easy because you're just doing it in 3 dimensions. You're only adjusting your latitude and longitude. Okay. Ski downhill to train Google Translate has 100 million parameters. Okay. What that means is imagine skiing downhill in a 100 million dimensional space. Okay. So each parameter is a different direction, orthogonal direction, perpendicular direction in this huge space. And you need to ski downhill in that space, adjusting all of these, not just latitude and longitude, but 100 million of these, or a trillion if you're doing training ChatGPT 4. Okay. That's hard. Okay? You can imagine that actually takes quite a bit of computational power. Okay. So that's what you do. Okay. What you do is you apply the inputs, you calculate the outputs. They're not going to be right. You take step downhill, you go a little bit downhill. Okay. And then you go back and you calculate it again, you adjust going downhill. You just keep doing that until you reach the bottom. Okay, where that's 0. It's okay, great. Let's just do the same thing in our flow networks, or a simple model for the brain vasculature. Okay, but there's a problem, which is that neural networks, they just live on the computer. They're not real. Okay, but we are trying to understand a system that is actually real. That meant that it had to be physics. Okay, what physics is that? I think we all have an intuition for it. Okay, so this is a picture of cars on a highway. Can't go tell whether they're going right to left or left to right. Okay, but you know this picture is basically right because the current of cars, number of cars per second, for example, coming in from here, coming in from there, is adding up. Okay, and no cars are created or destroyed as you go through this junction. Current here plus the current here coming in has to equal the current coming out. Okay, that's called a conservation law. Okay, it's given. That's what physicists call it. What goes in must come out is what physicists get fancy and call it a conservation law. It's also called Kirchhoff's law. Okay, and that's something that our system has to satisfy. And now here's the thing: that if I apply, it turns out that its flow network translates mathematically exactly into an electrical network of resistors. Okay, and I'm going to put it in the language of an electrical network. Okay, so the issue is, suppose I have a voltage source here, and I want to have a voltage out across this over here. Okay, I'm going to adjust all the resistances of the edges. That's adjusting the blood vessel diameters. I want to adjust these to go downhill in my cost function. But at the same time, as I'm adjusting the resistances, I'm changing the currents. Okay, and that means that I'm no longer obeying that conservation law. And so I have to go back and I have to fix that. I have to satisfy the conservation law. Okay? So at all points in this process, as we're adjusting resistances, we have to go back and make sure that all the currents are balanced at every node. Physics says you have to do that. Okay, that's something that an artificial neural network doesn't need to worry about. And it turns out that satisfying this conservation law is identical to minimizing the power the system is dissipating. Okay, so all right. So here's the process then that we do to train our model for the brain vasculature. I have a learning cost function, which is just, suppose we have a source here and we want a certain target pressure drop or voltage drop here. Compare what I'm going to call the free case, where I apply the source and I let the target be free to be what it wants to be. Okay, so that's a free case. I compare it to what I want. What came out here, I compare it to what I want. I square it because I want it to be positive, and then I start going downhill. I start skiing downhill. Am I skiing downhill? Here I'm adjusting resistances of the little shapes of the blood vessels by adjusting their diameter. Okay, so that's what you want to imagine, or the electrical resistances. Okay, but as I do that, at all points during that process, I have to also minimize the power that's dissipated in order to satisfy that conservation law. So what goes into a junction must come out. Okay, and so I had to do this over and over again. I take a step downhill, adjust my resistances. I ski a little bit downhill. Okay, it's again a very high dimensional space. It's the space of all of the resistances of all of the little blood vessels here. Okay, and then as I go downhill, I have to make sure that my currents are all balanced. I satisfy the current conservation law. Go a little bit more downhill. Okay, just keep doing that over and over again. So really, what you have to do in order to train the physical system, it's harder than training a neural network because you have to ski on two different landscapes at the same time. Okay, you have to minimize this thing. You want to ski downhill the learning cost function with respect to learning degrees of freedom that you adjust, pipe resistances. But at the same time, physics says, no, you also have to go downhill in the dissipated power by adjusting, for example, the voltages or the currents. Okay? So you have to ski in two coupled dimensional landscapes all at the same time. Okay? Right. So that does work. Okay. I'm just going to show you this example where I put a pressure drop or voltage drop. Okay, imagine my artery is here. I'm going to call that 1. Then I want the output here to be like 0.2 of what it is here. Okay. And initially starts out much smaller than that. Okay. Now I'm going to adjust the pipe resistances. I'm going to adjust all these edge resistances on each little edge here. Okay. And as I adjust them, the pressure here is going up. It's getting bigger and bigger. Okay. And then finally, it's going to reach the value of 0.2, which is what I wanted. Okay. This way that people use to train artificial neural networks can be harnessed to solve a real problem, okay, a real physical problem. Now, this is great. We're really happy for a little while. Because the problem with this is that it involved a lot of computation. Okay. So I'm descending on two landscapes at once, and to calculate the direction downhill, okay, I needed a computer. I needed it to go downhill in both the learning landscape and also the physical landscape. Both landscapes, I had to go downhill, and I had to use a computer for both of them. It was very computationally intensive. That meant that I could never, ever get to size of the brain vasculature of 1 million edges. Okay, we could do several thousand, okay, maybe even 10,000, but 1 million was just way out of range. Okay, so it's not scalable. We can't just make this, use this technique and make bigger and bigger systems that can do it. We need to know everything, because in order to do this, we need to know everything, exactly how all the blood vessels are connected together, all the diameters of all the blood vessels, all the resistances, in order to just evaluate them. And then we had to calculate the direction, which way is downhill in this very high dimensional space, million dimensional space. Okay. And then we had to be able to go in there with tiny tweezers and adjust resistances of all of them. Right. So if you imagine doing this in a real system in the lab, like, can't do this. That's a problem. So design by doing this, it's inherently what you would call a global process, and it requires processing. Okay, a lot of it. This is really a problem for neural networks too. Okay, so it turns out that the energy required to train neural networks is doubling every 3.4 months. Okay, as networks artificial neural networks have sort of invaded every part of our lives, right? They're all over the place. Right, they can do more and more. Why can they do more and more? Because they've gotten bigger and bigger. Okay, so if you compare neural networks in the 1980s to neural networks now, huge difference is size. Okay, but that's taking a lot of energy. So the energy, even after a network is trained, just to use it requires a huge amount of energy. I'm going to get to that. Okay, it takes now whole rivers to cool the data centers where these calculations are being done. They're invisible to us. Okay, but in 2022, right, data centers used more than 1% of the world's electricity. This is a problem. You know, artificial intelligence is going to run into a sustainability wall because of this. This is a problem not only for our problem, okay, but for neural networks. When we were doing this, we weren't worried about neural networks. Okay, we were worried about our problem, and so we started thinking about, okay, can systems, you know, learn these sorts of input and output relations on their own, but without a processor? How would you do that? We said, is that even possible? How could you possibly do it? It's like, well, you know, brain can do it. The brain's learning all the time, and it's not hooked up to a computer, right? Our brains are doing this on their own. So if we compare an artificial neural network to brain, right? Artificial neural network only exists on a computer. Brain doesn't need a computer. This is its computer. Okay. In the brain, learning is distributed among all of the neurons. All the neurons are updating themselves. They're figuring out how to update themselves without knowing every single thing about what every other neuron is doing. Okay? They're updating just based on this Hebbian learning rule, neurons that fire together, wire together. Okay. Because it's just learning is distributed among these neurons, it's incredibly robust to damage. So there's some people who have such severe epilepsy, have to have half their brains removed. They can do image recognition just as well as people with a brain, okay, for example. Oh, they can live normal lives. It's incredibly robust to damage. You know, in a way, if you damaged a processor, okay, it's all over. It's also incredibly power efficient because it doesn't need to do all that computation to figure out how to go downhill. The brain has about 100 trillion synapses. It doesn't have to adjust them. It doesn't have to do this calculation of skiing downhill in 100 trillion dimensional space. That saves a huge amount of energy. So if you think about a chat GPT, you ask it to generate text. That takes about 200 kilojoules. Okay. Generate an image actually takes 10,000 kilojoules. That's enough to drive typical electrical car 10 miles. Okay. Think about that when you ask, for image generation. Okay. It's not free. It's costing a lot. In fact, it's costing 5 times more than the adult brain uses in an entire day. Okay. And just think about what all the things that the brain is doing. Right? It's controlling our thought, our memory, of course, all of our senses, our motor skills, every single process, our heartbeat, every single process that controls our body. And it's doing that on only 2,000 kilojoules a day. Amazing. So I thought about it, I was like, wow, it's amazing. So can we take one step closer? Okay. And what I mean by taking one step closer is I want to be able to update my resistances of my little pipes, okay, without knowing what all the other pipes are doing. Is it possible to do that? That's called a local rule. Ah, thanks, Con. Thank you. All right. So that's possible. This builds on work done by Benjamin Scalier, who I don't know if is in the room, but also this work was done by postdoc, Naki Stern, who I think is here. And here's the idea. So I apologize. There's an equation here. Don't worry about it if you don't want to. It's not necessary. Okay, but if you like equations, then you can indulge in it. So what we want to do is we want to minimize. We want our free response to be the same as the desired response. Okay, so imagine instead of saying I want the free response to the desired response, say I want the power that's dissipated for the free case be the same as the power that's dissipated in what I'm going to call the clamp case, where I apply the response that I want. Okay? Because if those are the same, then the output of the free case will be the response that I want. Okay? So great thing about doing that is that if I look at the power difference, remember the power is what's minimized. And it turns out the physics tells you that that cannot be negative. Okay? And because it's not negative, I don't have to square it to make sure that it's not negative. And so I can just ski downhill on this. Okay, so these are just the equations for skiing downhill. And what it shows you is that I can just for each edge, I can just say, I can measure the voltage drop across each edge for clamp case, the free case, these, okay? And I want to adjust the resistance to bring them closer together. That's all. Okay, so each edge I just update based on what's happening at that edge. I don't need to know what all the other edges are doing to update this stuff. Okay, that's the key. And it turns out that there is a limit in which this is doing gradient descent. Okay, so it's like skiing downhill in this very high dimensional space, but it's doing this just by this simple rule instead. Okay, so so that's the idea. All right. But we do this. So on the computer, then the idea is that on the second thing, I can use this rule to update. I don't have to ski downhill my learning landscape. I'm just going to update based on this rule. Okay. But I still have to satisfy the conservation law. Current that comes in must be the current that comes out of every node, at every junction. Okay. And if I did this on the computer, okay, that defeats my purpose, right? But I still can't scale this up. Still have this problem. But here's the great thing about physics. This is why we love physics. Okay? Because if you did it in the lab, did it in real life, and physics will automatically satisfy this law for you, the conservation law. You don't have to lift a finger. Just apply the voltages, okay? And physics will make sure the current that comes out in and out in every node will be the same as the current that goes out. It does it really fast. Okay? So it's free. Okay? That's great. All we need to do is figure out how to do this in the lab. Okay? That's not so trivial, it turns out, how to implement this learning rule in the lab. So this is where Sam Dillavu, who might be here in the room also, and Doug Durian is here. Come in. Okay. So they realize, okay, you can buy these little, let's do it in electrical version. Okay. You can buy these little digital variable resistors that can take on 128, for example, different resistance values. Okay. Now I need to compare the voltage drop across each edge. I apply the boundary condition where I just apply the source. And I have to compare that to what happens if I apply source and the desired target, the clamped case. Okay. There's no way to do both of these on the same network at the same time. It's just not possible. So a clever trick here is to build identical twin networks. So you have one network here, okay? And then it has its identical twin. Every resistance on every edge is the same at all times, okay? Now, the bottom network, you apply the source, but not the target. on the top one, you clamp it, you apply the source and the target that you want. Okay. And now each edge, it's really a set of identical twins, an identical twin pair. Okay. And here's what it looks like on a breadboard. There's the free variable resistor. There's the clamped one. Okay. And then there's other magic, which, okay, don't ask me, I'm a theorist, but my collaborators can tell you. What it does is it compares a voltage drop across them and it updates the resistance to make this difference get smaller. Okay. So didn't even do it. It didn't even implement the exact learning rule. It did an approximation to it. Okay. So here's the first generation. It had 16 of these edges, which are these variable resistors, identical twin pairs, and their nodes, junctions, where they come together. For each junction, you have to satisfy the conservation law, okay? And then each edge is this variable resistor that's adjusting using this rule, okay? So this only had 9 junctions and 16 edges, but it could do something that we were very proud of. Of course, computer scientists turn up their nose at this, but we were very proud of it. It could classify this thing called the iris data set. So what this is you get 4 measurements of the irises, the length and width of the petals and sepals. And then there were 3 different species of iris. Okay. The idea is based on these 4 measurements, classify them correctly into the 3 different species of iris. Okay. And some poor guy went around and did this for 150 flowers, 50 each of each species. Okay. So now this is the idea. Turn these measurements of length and width into voltages. Okay, so there's a ground. Okay, let's set a ground. And then I have 4 nodes where I feed in these voltages comparing to these measurements. Okay, and then there are 3 nodes, 1 for each species of iris. Okay, and the idea is that if it's species 1, this one will light up. Species 2, that one will light up. Species 3 will light up. Okay. And what you see is this is the classification error. As you train it, it goes down. The system actually classified these things. And it did as well, did it about 95% accuracy, which is about as well as you can do with a linear classifier on the computer. Okay. So this little circuit actually worked. It classified this stuff. And it can learn just one thing after another. Okay, I classify these irises. Okay, forget that. Now I'm going to apply 0 volts here, 5 volts here, and I want 3 volts there. Learn that. Okay. This is the error going down. Then change my mind. No, learn something else. Okay. Ground here, some 5 volts here. Give me 2 volts here, 3 volts here, for example. Learn that. Okay. Give it more and more complex things. It learns one thing after another. Same circuit. So all you're doing is you're changing the voltages that you're applying to it. You're changing what you mean by free and clamped, different tasks. It's the same circuit. So this old dog can learn one new trick after another. Okay. This is great. Very happy for a little while. Okay. Because then turns out this, because the network is just made out of resistors, that's really limiting. You can only learn a limited number of tasks. In fact, when artificial neural networks first came about, people got all excited, and then they realized, oh, there are lots of things that they can't do. They were linear, and everybody gave up. Not everybody, but almost everybody gave up, and there was sort of the hiatus for 10 or 15 years until people started making them nonlinear and then started making them bigger. Okay, so you need nonlinearity. And so it's our second generation. Second generation is actually nonlinear. Okay, uses transistors. It's a transistor-based design. Okay, what that means is now resistance depends on the voltages on either side. So each edge, right? Each resistor has a node at each end of it, and the voltages on those nodes will actually have a part in determining the resistance there. Okay, so that's because it depends on them. It's a nonlinearity. It's what's called a nonlinearity. Don't need to worry about it. This system, this is where colleague Mark Miskin, who might be here, came in and designed this version, um, uh, implements the exact couple learning rule. And it's amazing. Here's a system. Oh, shoot. I forgot how many nodes. I think 25 nodes, 25 edges, 16 nodes, 25 edges. The time that it takes for this thing on a breadboard is already 10 times faster than doing the same thing on the computer. Why? Because satisfying that conservation law, okay, takes a long time on the computer. It's really hard to figure out. The problem's nonlinear. Okay, it's already 10 times faster than to do the same thing on the computer, even at this size. And that advantage just grows as the system gets bigger. Okay. So, so it can do things that our original system couldn't do. So here's an example. These are my training points. I have these blue points. I'm going to say these are blue. Okay. And then there are these points. I say these are gold. Okay. And this is, so for a given, I tell you a given input, a given out into node 1, given input into node 2, input voltage. Okay. And that specifies the coordinate of this point. And I say, I want these to be called gold points and these to be called blue points. Now, initially, you send it through the network, okay? The background color tells you the answer that comes out of the network. It's not right, because what you want is a blue color for these blue points. You want a gold color around these gold points. Okay, and the boundary between blue and gold is this black line. It's not at the right place. It should be somewhere here. Okay, now let's train it. Let's let it go. Okay, and eventually finds it, settles down, it finds it. And our original linear network could never have done it because it couldn't have, this couldn't have been curved. It would have to be a straight line. That's why it's called linear. Okay. So the fact that it found this curved boundary is something that our original system couldn't have done. All right. So, and that's what makes modern, this nonlinearity is the thing that makes modern AI so powerful. All right. So this is a tiny system, right? Really, how can we compare it to artificial neural networks? We have 1 trillion parameters. Okay. Here we have, we had, I think, 25 parameters or 32. I can't remember. Okay. Which are the individual resistances on these. Okay. Problem is, people have been trying to build physical systems that can carry out these machine learning tasks. They're like neural networks that can do this. Okay. The problem is manufacturing error. Any little mistake and messes everything up. Okay. Great thing by having this distributed learning, each resistance, each resistor or nonlinear resistor doesn't have to know what everybody else is doing, is that the system can learn around defects. So here it is. Okay, here's our original system. It learned something. Okay, so the error went down. And now we go in and we snip that edge. Just cut that out. Oh, it doesn't work anymore. Okay, the error got big again. Okay, but it just went ahead and trained itself and it learned it again. Okay. Now I flip the gold edge. Uh-oh. Okay, the error got big again, but now it trains itself and went down again. It learned it again. It just learns around these defects. Then some of them you cut and it actually makes no difference at all. You don't even have to train it again. It just goes right on through. Okay. So this system of 16 edges, we are able to remove 5 of them. It could just learn around it. And in fact, Sam had a horrible time bugging these circuits because they kept working. Okay. Put it in and do it. Worked. And then he'd change it around and change it around and then everything would work. And then suddenly just change which ones he chose as his inputs and outputs. And it wouldn't work. Like, why? It was a defective edge. Okay. The system just learned around it. So that means that you don't have to manufacture it perfectly. You can tolerate defects. You don't have to manufacture it perfectly, and it can still learn. Okay. So that's what we're doing. Okay. We want to scale this up. So the robustness to damage means that it's be manufacturable. Now, that's because the learning is distributed, right? All these resistance changes are calculated in parallel on every edge. This is very fast. Okay. And it also means it doesn't take much power. So it turns out that even in our current breadboard version, okay, the energy that it takes to use the trained neural network, okay, once you've trained it to apply the voltages and get that desired outputs, okay, it's about 300 picojoules. And that's really in the ballpark doing the same thing, same task on a neural network of the same size on the most energy efficient chip in the world. Okay. So we're already breaking even, and we haven't even tried to lower the power. You know, Aki Stern, my postdoc, has done very clever things to figure out how to use these in ways that even use lower power solutions, okay, where we can get even lower power solutions. We haven't done any of that optimization yet, and we're already breaking even. Okay. So the next step, we have these printed circuit boards. Okay. So instead of having a breadboard where you assemble everything on by hand, it's now printed onto this, each edge. And so now it was a heroic effort to build this network, this initial network of 16 edges, and then the second one of 25 edges. That was a lot of work. Okay. But now I can just print them out. It's money, just in short supply. Okay. But this we can, make networks of 100 to 200 edges. The great thing is because it's transistor based, you can just use totally standard microfabrication, and we should be able to scale up to 10 million edges on a chip, a tiny chip. If we do that, and the time that it takes to calculate the outputs given the inputs should be of order nanoseconds. Right now it's tens of microseconds. We can speed it up. We should be able to speed it up by 4 orders of magnitude. And then the energy to calculate outputs given the inputs should be of order 10 picojoules. Okay. Really cheap. So this is exciting. If you get up to 10 million edges on a chip, it works. Okay. It should be, doing some serious machine learning tasks, AI tasks. So, but at much lower energy cost. So that's the message, it's a massively scalable design. And so, it's possible that it would actually be able to replace artificial neural networks. Certain applications where you care about how much power you're using, there's high chance of damage. Mark Miskin, who developed the second generation, is really interested in this for putting these on little robots, okay, where you really don't want to have a little processor on every robot. You want it to be small, not to use too much power, for example. So let me just finish up with all the people who did this. And thanks for your attention.
Have questions?
Let me say too that in brains, right? Learning is a phenomenon that just comes about. It just emerges, the interactions of all the neurons. And that's the same thing in our system. In our system, it just emerges from the interactions of all these edges that are all being adjusted individually. Learning, it's a collective phenomenon across the whole system. How can it emerge? Emerges because of the conservation law. Because even though I don't need to know what every edge is doing in order to adjust myself, okay? I have to be connected to what every other edge is doing because I have to satisfy that what comes in will comes out at every edge. And that's what couples the system across everything and allows learning to emerge as a collective phenomenon in this system. So it's fascinating to study from a physics point of view, to study that process of this emerging, and we're incredibly excited about it. Okay, thanks. Question. Yeah.
You're talking about learning, and you had your graph when there was a stasis, if you will. Does it remember things? Is memory involved, or is it only learning?
No, once you have the resistances, if you hold those resistances, then it remembers it. So this is what's called computed memory. There's this thing called the Van Neumann bottleneck that when you do calculations, you have to shuffle things in and out of memory all the time. Takes a lot of power. Here, the memory is in the resistance. So as long as you have that, remembers it. That's a great question. Yeah.
This is going to sound consistent. So, on the subject of learning versus memory, I'm assuming that machine, something that's not our brain, can retain memory, but the human brain always do that. But it doesn't. You know what the difference is there?
Actually, yeah, let me repeat the question. Like, when you have a machine learn something, it should remember it forever, but the human brain forgets things. It turns out the neural networks forget things too. Okay, you train them to do something else and forget what it knew before, and it actually forgets it often in a very catastrophic way. There's this thing called catastrophic forgetting. Okay, our networks, our linear networks, forget things right away. As soon as you show it a new task, it forgets the old one. Okay. The nonlinear ones ought to remember it better. Okay. But, how well they can remember it. This is fascinating question that that we want to study. That was a great question.
Curious, so you initialize the resistors in some random configuration, and then it learns over epochs. Did you ever initialize it in some things that get stuck in local minima, or does it always go to the same configuration each time from the different initial conditions?
Yeah. So the interesting thing about this, the question is, how much does the set of resistances that you end up with depend on your initial conditions? If you have your initial resistances on every edge, you have to set them to something. And you sometimes get stuck and not be able to train and get rid of that error, get it the noise floor. Okay. By getting stuck in what's called a local minimum. And if you start with different initial conditions, you always end up with the same answer, the same resistances on each edge. And the answer is these networks, the regime that we're using them, are what are called over-parameterized. It's the same regime that you run artificial neural networks in. You have a lot more parameters to play with than you actually need. Okay. And what that means is that there are many, many solutions. So depending on my initial resistances, okay, I will end up with different sets of resistances to solve the same problem. Many, many ways to give the desired output. Okay, there are many different sets of resistances on the edges that will give me the correct output. Okay. Can we get sometimes stuck? Yes, we can sometimes get stuck in local minima. Again, that becomes less and less likely as we make our networks bigger compared to their task complexity. That's key. That's why you want big networks. That's why, ChatGPT-4 has 1 trillion parameters. It's so that you don't get stuck a little, you want to get down to the bottom of the slope, but you got stuck somewhere going downhill. Okay. Yeah. To avoid that, you want to have many, many very high dimensional space.
What sort of everyday things would this be applied to, aside from just conserving energy instead of using the processor?
Well,
Could you repeat the question?
yes, sorry. What kinds of everyday things could this do? Well, we don't know if it all works, okay? This is a different problem from what artificial neural networks. Artificial neural networks, actually theorems that show that you can solve any problem, no matter how complex it is. Any input-output problem, the kind of nonlinearities that people use. We don't know whether the nonlinearities that we have here are enough, okay, to do everything. Suppose they are, okay? They are, and in principle, this can do anything that an artificial neural network can do. Any kind of task. Same idea. You just apply voltage inputs, voltage outputs. So you can translate an image to a bunch of voltage inputs. Then out comes this voltage output that tells you if it's a cat or a dog, for example. But anything that artificial neural networks do now in our lives, it's good to. Now, I should make a distinction. There are different kinds of learning. There's a kind of learning called supervised learning, where you know the answer. When you're training the network, you say, no, that's supposed to be a dog. Okay. So supervised learning, that's what these systems are set up to do. Okay. There's also a very important kind of learning called unsupervised learning. Okay. Where you don't tell it a label. So, and there are things they're called restricted Boltzmann machines. Okay. So for example, Netflix, when it makes recommendations, or Amazon, when they make recommendations, they actually use unsupervised learning. These sort of restricted Boltzmann machines. So my postdoc Marcelo, I think, is here, came up with a way to implement restricted Boltzmann machines on similar circuits, not the same, but very similar. So if we can build those, then we would have a way to do unsupervised learning too. So yeah, we need his money. So, there is actually an incubator VC firm that gotten in touch with us, and they're actually building prototypes now, and develop prototypes to do vision tasks. Okay.
I just wonder about other applications where we make machines that learn to interact with and do things, not just do computation. So I'm thinking about going back to your beginning about the brain.
Yeah.
Is there a way to make a version of this out of fluid channels? I mean, the analogy between resistance and current. Is anybody thinking about making a learning vascular network physically?
Yeah. So that's an interesting question. We actually have, yes, an NSF grant, a group grant to Penn, funded to try to do exactly that. One thing that should be able to do, because electrical networks, circuits are identical to fluidic circuits. Okay, what we should be able to do is train it on our chips. Okay, then print out a microfluidic device which has the right diameters for all the little pipes. Okay, it should then be able to do the task. So that we should be able to do, and that's part of our grant. That we think we can do. But to actually then have all the pipes be able to adjust their diameters, that's a little harder. To say that it's not just the fluid version that we can do. We can do this in a mechanical version. Okay, where you apply strains, forces here, for example, your fingerprint by forces. Okay, then that creates the system recognize your fingerprint and unlocks the door. Okay, whatever. Should be able to do that. A mechanical version where you have mechanical edges Okay, which example, you can think of them as springs. You adjust the stiffnesses of the springs on their own according to a similar rule. So we can generalize this to that case. And in fact, Lauren Altman, who is here, and Doug Durian have a first sort of generation of a simple system that could do that. Okay, not scalable yet, but okay. Yeah, we're working on that. Thank you all for coming.